What if I told you that a single number, literally just changing 0.2 to 0.9, could turn a boring, repetitive AI into a wildly creative writer? Or that the same model answering your question has access to thousands of possible next words, and there is a hidden lottery happening millions of times per response to pick each one? Most people using ChatGPT, Claude, or any LLM have no idea that they are sitting on a control panel with knobs labeled temperature, top P, and sampling strategy. Today, you're going to understand exactly what these knobs do, why they exist, and how to tune them like a pro. Before we touch any parameters, let us understand what an LLM actually outputs. When you type a prompt, the model does not magically produce text. It produces a probability distribution over its entire vocabulary. Imagine a bar chart with 50,000 bars, one for each possible next word. Some bars are tall, those words are likely. Most bars are tiny. Those words make no sense in context. The model's job is done once it hands you this chart. Everything else, temperature, top P, all of it, is about how we read this chart to pick the actual next word. The most obvious approach? Just pick the tallest bar every single time. This is called greedy decoding. If "the" has a 30% probability and nothing else comes close, we pick "the" and move on. Sounds reasonable, right? But here is the problem. Greedy decoding produces the same output every time for the same input. It is completely deterministic. And worse, it often gets stuck in repetitive loops, generating phrases like the, they, or endlessly repeating itself. What if instead of always picking the winner, we held a weighted lottery? Words with higher probabilities get more lottery tickets, but even low probability words have a chance. This is random sampling, also called ancestral sampling. Now our outputs become diverse and interesting. The same prompt can produce different completions each time. But there is a catch. Sometimes those low probability words win the lottery, and suddenly your professional email contains the word banana for absolutely no reason. Temperature is how we control the chaos. Mathematically, we divide all the raw scores, called logits, by the temperature value before converting them to probabilities. When temperature equals 1, nothing changes. You get the original distribution, but drop it to 0.5 and something magical happens. The tall bars get taller, the short bars get shorter. The distribution becomes sharper, more peaked. Raise temperature to 1.5 and the opposite occurs. Everything flattens out, giving unlikely words a fighting chance. Temperature 0? That is essentially greedy decoding. The highest probability word wins every time. Let us make this concrete. Prompt: the capital of France is? At temperature 0.1, you will get Paris every single time. The model is confident and we are amplifying that confidence. At temperature 1.0, you might occasionally see Paris, which is also known as slight variations emerge. Crank it to 2.0 and suddenly you might get technically disputed or even a beautiful city. The model starts ignoring what it knows to be most likely. Temperature is not about making the model smarter. It is about how much we trust its confidence. But here is where temperature hits a wall. No matter how low you set it, every word in the vocabulary still has some non-zero probability. That word banana in your legal document? With pure temperature scaling, it can still appear. Just rarely. And when you are generating thousands of tokens, rarely starts happening. We need a way to completely eliminate the nonsense words from consideration, not just make them less likely. This is where truncation methods come in. Top K filtering takes a simple approach. Keep only the K most likely words, throw away everything else, then sample from what remains. Set K to 50, and only the top 50 words even get considered. This guarantees no wild outliers. But top K has a fundamental flaw. Sometimes the model is very confident. Maybe only 5 words make sense. Other times, 500 words could reasonably follow. Using a fixed K of 50 means you either include garbage when the model is confident or exclude good options when it is uncertain. Nucleus sampling, or top P, fixes this beautifully. Instead of keeping a fixed number of words, we keep the smallest set of words whose combined probability exceeds P, set P to 0.9, and we keep adding words from most likely to least likely until their probabilities sum to 90%. When the model is confident, maybe only 3 words make the cut. When it is uncertain, maybe 300 do. The nucleus, the core set of reasonable words, adapts automatically to the model's confidence. This is why top P has become the industry standard. Let us walk through top P equals 0.9 with real numbers. Say our top words are walked at 40%, run at 25%, sprinted at 15%, jogged at 8%, crawled at 5%. We add them up. 40 plus 25 is 65, plus 15 is 80, plus 8 is 88, plus 5 is 93. We have crossed 90%, so our nucleus is these 5 words. We renormalize the probabilities to sum to 1, then sample. Everything outside may be teleported at 0.1%, gets 0 chance. No banana surprises. Here is where it gets interesting. You can use both together. The standard approach is to apply temperature first, reshape the distribution, then apply top P to truncate it. Low temperature with moderate top P gives you focused, consistent outputs with a safety net against outliers. High temperature with tight top P lets creativity flow but keeps it bounded. The sweet spot depends entirely on your task. OpenAI's API, Anthropic's API, most inference engines, they all let you set both parameters independently. Let me give you a practical cheat sheet. For code generation, go cold. Temperature 0.1 to 0.3. Top P around 0.9. Code has one right answer. You want the model's best guess. For factual Q&A and summarization, stay cool. Temperature 0.3 to 0.5. Top P 0.9. Some variety is fine, but accuracy matters. For creative writing and brainstorming, warm it up. Temperature 0.7 to 1.0. Top P 0.95. For truly experimental, weird, boundary-pushing content, temperature 1.2 plus, top P 0.9, but review everything carefully. 3 mistakes I see constantly. First, thinking temperature makes the model think harder. It does not. The model's computation is identical. You are just reading its output differently. Second, setting both temperature to 0 and top P to 1.0, then wondering why outputs vary. Some randomness exists in floating point operations. Use temperature 0 OR top P around 0.1 for true determinism. Third, cranking temperature sky high for creativity. Past 1.5, you're not getting creativity. You're getting incoherence. The model's training did not prepare it for those probability landscapes. Before we wrap up, let me plant some seeds for deeper exploration. Repetition penalties add negative weight to recently generated tokens, essential for longer outputs. Frequency and presence penalties in OpenAI's API work similarly. Beam search keeps multiple candidate sequences alive, useful for translation tasks. Contrastive decoding compares outputs from models of different sizes. And classifier-free guidance, borrowed from image generation, can steer outputs toward desired attributes. Each of these builds on the foundation you now understand. So here is the complete picture. An LLM gives you probabilities. Temperature reshapes those probabilities. Low squeezes them sharp, high spreads them flat. Top P truncates to a dynamic nucleus based on cumulative probability. Top K truncates to a fixed count. You apply temperature first, then truncation, then sample. For most tasks, start with temperature 0.7 and top P 0.9, then adjust based on results. These are not magic numbers. They are principled controls over the fundamental randomness in language generation. Let us lock in what you have learned today. First, LLMs, output probability distributions, not text. Everything else is about how we sample from that distribution. Second, temperature controls the shape of probabilities. Low means focused and deterministic. High means flat and random. Third, top P dynamically selects a nucleus of reasonable words based on cumulative probability, adapting to the model's confidence. Next, in the AI track, we are diving into attention mechanisms, the actual architecture that lets transformers understand context and relationships in your prompts. If this video helped demystify how AI generates text, hit subscribe so you do not miss it. And drop a comment below. What temperature and top P settings have given you the best results for your use case? I read every comment. See you in the next one.